Hello and welcome to all of you. This presentation is about mobile robots that handle logistics operations together with humans. I want to show some of the novel developments which we believe will bring robotized logistics operations to the next level. I will primarily refer to autonomous forklifts that operate in complex environments where they share space with workers. In particular, I want to explain a concept that facilitates the gradual introduction of fleets of autonomous forklifts into existing factories or warehouses through a self-installation process, which is called integrated automatic deployment. In my research group, we have accumulated more than 15 years of experience in collaborative projects with industrial partners who have an interest in autonomous mobile transport robots. On this slide, you can see some of the vehicles we have been working with, ranging from compact, originally hand-driven pallet trucks to large wheel loaders or mining vehicles with 40 tons or more. All of these robots have to pick up something at point A, bring it safely, reliably, and efficiently to point or area B, and place it there. In a complex environment where there are also humans or human-driven vehicles, driving to point or area B is similar to autonomous driving, and indeed, we are largely addressing the same general problems. However, an important difference is that we can assume that the environment is semi-controlled. This means that the company, which is responsible for operations, can introduce guidelines that make some tasks easier for the robots. For example, requiring people to wear safety vests so that the robots can detect them more easily. In this presentation, I will focus on autonomous mobile forklift trucks and warehouse logistics to illustrate the general concepts we develop. You can see the forklift trucks with which we work in the top row of the images on this slide. Now let's look at robotized intralogistics in a warehouse. Here's the concept image of the use case we are addressing in the currently ongoing European project, Iliad. A fleet of forklift trucks receives orders from the warehouse management system, identifies how to most efficiently schedule and distribute the tasks, and moves the truck, say AGV02, to the next shelf that stores the product on their list. There, for example, in picking area 01, the logistics robots pick up goods, put them on a pallet, and move the pallet to its destination. As mentioned before, the environment is shared with humans, and there are also human-operated trucks. This also means that the environment is dynamic, that it is changing all the time, and that the robots need to observe these changes as they do not result from their own actions. According to our industrial partners, a key issue that hinders the introduction of autonomous systems in such a scenario is the deployment process, the installation of robots in their target environment. It currently takes a too long time from the arrival of the robots to their first mission, and deployment is carried out by highly specialized engineers who frequently don't come back from customers who simply hire them. What is needed is a simplified, easy, autonomous deployment process, which should not rely on additional infrastructure, which should use existing knowledge, and which then allows adaptation to changes during runtime. Let me now briefly mention a few of the key concepts with which we can deploy and run a mission within an hour compared to hundreds of hours with other systems. First, the robots localize themselves without the need to install additional infrastructure in the environment, such as active beacons or markers on the floor, for example. In panel number 1, you can see the precision with which a robot can position itself. The two pictures are composed of 10 individual photos, and for each of those photos, the robot was first moved to another place and then instructed to drive to the exact same location again. Since the 10 images were taken from the same position, the amount of blur in the combined photo is an indication of the improved positioning precision with our method that is shown on the right. The improvement between the left and the right picture goes along with a qualitative difference. The autonomous forklift truck on the left will often fail to pick up a pallet at the target location, while this is not the case on the right side, where the end position varies by less than 1 centimeter. Panel number 2 visualizes how the forklifts can use existing information in order to speed up the deployment process. Often there are prior maps of the environment available, such as a floor plan or an emergency map, or even maps created by other robots in the past, or simply a sketch, as in this example. We have developed ways to combine the information collected by the robot map here, with information that is in prior maps. Although these prior maps are usually outdated, don't include any furniture, and are metrically incorrect. This allows to auto-correct both the robot map and the prior map, and also to auto-complete the robot map. In other words, to extend it beyond the area explored by the robot. And this saves valuable exploration and mapping time. Further components of our autonomous deployment procedure are shown on this slide. In panel 3, you can see that fast deployment is supported by an automatic calibration procedure, in which an autonomous robot learns how its sensors are positioned with respect to each other by learning how the measurements best fit together. This can be seen by the emerging crispness of the shown map of the environment here. We also try to give the autonomous vehicles a sense of introspection. Panel 4 is an attempt to visualize that introspection allows the robot to reason about inconsistencies in its knowledge about the world. For example, our autonomous forklifts can identify parts of the environment, parts of their map of the environment that appear to be wrong. And they can then try to automatically correct the map, or at least mistrust this part of the map. Now, it is important to notice that an autonomous deployment process can run repeatedly or even continuously, which facilitates long-term operations as it allows the robotic system to adapt to changes during runtime. Running the deployment process frequently is, however, just one way to address that things change constantly in the environment. As a consequence of changes, the most efficient way to carry out an order will also change, maybe due to a congestion or because a passage is blocked by a worker. Therefore, we want autonomous transport robots that are competent in handling changes. They should be able to recognize changes, to learn from observations about spatial motion patterns. They should also be able to predict, in particular, human motion, and they should be able to use all this information for their planning. Now let's first look at learning of spatial motion patterns. What you see here on the right is a geometric map of a warehouse. The geometric map are the black areas in the background. In addition to the geometric map, you can also see a so-called map of dynamics, which is visualized by arrows that show the motion patterns the robots have learned by observing people and human-driven vehicles over 6 days. What we see here is that the autonomous forklift trucks have discovered that the human-driven forklift trucks follow a right-hand traffic rule in the highlighted corridor here in the middle of this figure. And they have also learned that people walk around the stack of shelves here in the top part of the figure in clockwise direction. It is obvious that this is useful information which needs to be taken into account for planning the motion of autonomous vehicles. Next, for safety, efficiency, and legibility, autonomous robots need predictive planning capabilities. We were hit by the importance of predictive planning initially, not in a project with robotic forklifts, but in another European project in which we developed an autonomous guide robot at Schiphol Airport in Amsterdam, which you can see here. The general idea is that passengers show their boarding pass to the robot, which then guides them to their gate. One of the key insights from this deployment at Schiphol Airport was that social navigation, as we had imagined it, stopped being functional already in moderately dense crowds. It turned out that it is necessary for the robot to be able to predict possible human trajectories better than just to project their current motion linearly into the future. Our approach to predict human motion for the coming 3 to 15 seconds is visualized here. Given the structure of the environment and possible goal locations, our approach models goal-directed behavior of people as approximately rational motion. It can predict different possible future trajectories, as you can see here in the middle, and it can actually take into account social forces. So repulsive social forces that keep people from getting too close to each other, and attractive social forces that keep people in the group staying together. Now I talked about how robots can predict the motion of people, but left out an important step, which is to detect and track people in the first place. And for this task, I switch back from the uncontrolled public area at Schiphol to semi-controlled industrial environments. The next slide here shows error modes of camera-based people tracking solutions, which tend to fail in case humans are seen only partially, if the camera is exposed to strong light, or if people do not appear in a standard upright pose. It also shows that people often wear safety vests, as can be seen, for example, in the top left picture. Since safety clothing with reflective markers is often mandatory at the workplace, or it can be made mandatory, we developed an active people tracking camera that heavily uses artificial intelligence. This camera detects people extremely reliably as long as they wear reflective safety clothing, largely without suffering from the problems shown here. This active safety camera is called Emitrace, and it is on the market since last year, distributed by the startup company Retenure, a spin-off of my group. In the pictures below, you can see that the camera detects reflective safety vests, distinguishes them from other reflective objects in the environment, and is thus able to detect multiple people in different poses, and works even outdoors if it happens to be exposed to direct sunlight. The camera is intended to be used on autonomous vehicles, but also for driver assistance, as it's shown in the video here. The camera is mounted in rear direction, and an additional warning lamp is mounted in the cabin. Usually, the camera will indicate that its field of view is free of people, but it will warn the driver not to start driving backwards if a person entered the safety area to the rear side. So this brings us to the end of my presentation. And there I'd like to show you a video to wrap up that summarizes the European project Iliad, in which most of the results I showed in my presentation were obtained. The video shows footage from a deployment of the Iliad system at an Orkla food distribution center in Sweden.
Iliad is a Horizon 2020 European Union funded research and innovation project. In this project we are 9 partners, 5 from industry, 4 from academia, and we come from 4 different countries and work together to develop solutions in which mobile robots, mobile autonomous forklifts work together alongside with humans, for example in warehouses, to handle the logistics, where they bring goods from one place to another so that, for example, they put them on pallets and bring them to the place where they are needed to. They self-deploy, which means you bring them into the environment and then they learn how to optimize their behavior. They learn how people actually behave there. They interact safely. There's a lot of consideration of safety, and they recognize the goods and handle them with a dual arm system. So Iliad is full of innovations, and maybe on the whole, the most important one is that Iliad comes with a solution that allows the gradual integration of these autonomous forklifts into existing processes. That means that a company does not have to make a huge investment, like set up a new building or like change the processes altogether. But it also means that the robots integrate with people who are working there. So in a sense, Iliad is also a suggestion for a job-preserving transition to automation.
Iliad will contribute to making warehouse logistics both safer, more efficient, and also more comfortable. But the technologies that we developed in Iliad will also have applications in many other fields and will make robots more easily available in applications such as self-driving cars, home service robotics, search and rescue missions, and so on. We also have a two-arm manipulation system that can pick objects very much like a human would do. So with the same two arms and same two grippers, we can pick many different kinds of items without having to reconfigure or change the tools. So ultimately, the aim of Iliad is to make robots more easily available that can help people with dangerous and heavy and difficult tasks.
As a promotional video of my university, the video is focusing on achievements at Örebro University and the deployment at Orkla. In the end, I therefore like to acknowledge that I could only show a small part of the contributions in Iliad in this presentation, and that I'm naturally somewhat biased in selecting our own contributions for such a presentation. If you'd like to know more about the projects, just scan the QR code on this slide or send us an email. I'd like to thank all the researchers in the consortium, some of which are shown on this slide here, and I'd like to gratefully acknowledge the funding we received from the EU. Finally, thank you very much for your attention.